While studying viscosity, many a times we come across situations wherein the flow of the fluid suddenly becomes turbulent or random, let us say. Okay. So herein, this is a laminar flow situation and the fluid is flowing in a pipe in a laminar manner. Okay. And this is the turbulent flow situation wherein we don't know what is happening. All the streamlines, if they exist, are intersecting and all the molecules of the liquid are crossing each other. Okay. So there is this number called as the Reynolds number, R, capital R, which is defined as rho v d upon eta. Rho is the density of the liquid, v is the velocity. Okay, so this is the density, v is the velocity, and d is the diameter. Eta happens to be the coefficient of viscosity. So this number, which is called as the Reynolds number, this tells us essentially whether turbulence is happening or whether the fluid is flowing in a regular laminar or streamlined manner, basically. So whether it is smoothly flowing or it is turbulently flowing, like so. All right. So usually what is considered is as follows. As a rule of thumb, when Reno number or Reynolds number is between 0 and 1000, okay, if it is between 0 and 1000, then this implies smooth flow. All right. If Reno number is going to be between 1000 and 2000, that means turbulence is beginning. Okay, so this is the beginning stages of turbulence. All right, so we have got the third case wherein, let us say, if the Reno number is between 2000 and 3000, then this means that the flow is really turbulent. So this is turbulent flow. All right, let us look at an example of fluid flow. So here we can see that the Reno number up to 1000, when the Reno number is up to 1000, the fluid is smoothly flowing around an obstacle, basically, and the streamlines, so as to say, are somewhat intact. Okay. And let us say if we increase the Reno number beyond, let us say 2000, then turbulence begins, and then the fluid molecules or the parts of the fluid molecules intersect with each other. A good way to visualize turbulence would be visualize the flow of fluid from a tap. As we turn on the tap, the fluid is relatively flowing smoothly, and as the water hits the floor or the bottom of the basin or the container, okay, at that point suddenly the water diverges into different paths, basically. So that is called as turbulent flow. So Reno number is essentially used to understand whether the flow of fluid is going to be turbulent or whether the flow of fluid is going to be streamlined or smooth. Okay. Let us try to analyze the dimensions of Reno number over here. So Reno number happens to be, okay, here we have seen Reno number happens to be rho v d upon eta. D is the diameter of the uh, column of fluid or diameter of the pipe through which the fluid is flowing, basically, we can say. Okay, so the dimensions of Reno number, if we were to try and find out the dimensions, what do we get? So the dimensions of density are nothing but mass over volume. Now volume I am choosing to write as area, okay, into length. Velocity is length per unit time, and diameter d is just length, and eta. So what are the dimensions of eta? We have this formula, force is equal to eta A dv upon dx. So we can say that the dimensions of eta are the dimensions of force. So force is what? Mass dv upon dt. So dimensions of force divided by area dv upon dx. So dv is going to get cancelled over here, and then this dx will come up. So it is like mass velocity, okay, upon area. So that is what eta is. So in the denominator we have got mass velocity upon area. So this right over here is velocity, so this will get cancelled with velocity, mass will get cancelled with mass, area will get cancelled with area, and length with length. So what do we get? The dimensions of Reno number are null. So basically that's why we are not mentioning or specifying any units. Okay, so this has got null dimensions. So it is just a number, that is why it is called as Reno number essentially. Alright.